This MEB video is about how to read and interpret a TXY or a PXY diagram. I'll start by defining what it even is that we're looking at. So PXY and TXY diagrams are plots that show bubble point and dew point temperatures, that would be the TXY, or the bubble point and dew point pressures, that would be a PXY, as a function of the overall composition. In other words, those bubble point and dew point calculations that I showed you in the last video are already solved and plotted here such that you can see visually what the bubble points and the dew points are. First thing that you have to know when you are looking at a TXY or PXY diagram is where liquid and vapor are. These two diagrams are for benzene toluene, two chemicals that are oftentimes studied because they are known to be an ideal or very close to ideal system. These PXY and TXY diagrams are labeled already for you in terms of where the vapor and the liquid are, but in general, that will not be the case. So for a TXY diagram, once again, I don't memorize this, but the top section of the plot corresponds to vapor. So everything I'm shading in light blue is the vapor section. Similarly, for the PXY, vapor is the bottom. Now, why does it flip? Why is it the top of the TXY and the bottom for the PXY? And the reason for that is if you just think about it, at high temperatures, things tend to vaporize. Similarly, at low pressures, things also tend to vaporize. So I just like to think of these things conceptually, like I said. If something is at a high temperature, it will be a vapor, or a low pressure, it would be vapor. Now, on the other side of the plot is the liquid. So I'll shade the liquid in a different color, in a darker shade of blue. So this part that I'm shading now is the liquid part of the plot. And for the same reasons that the vapor is high for temperature and low for pressure, same reasons apply for why liquid is low for temperature and high for pressure. As temperature goes down, things tend to condense, or as pressure goes down, as pressure goes up, things tend to condense as well. The interesting part of the TXY diagrams and the PXY diagrams is in the very middle. So that would be the region between these curves where I have phase equilibrium applying. So this part of the plot is where vapor-liquid equilibrium occurs. So these lines have names on the plots where I'm going from vapor to equilibrium is the dew point curve. So the top one on the TXY is the dew point curve. That is because if you imagine that I have a vapor mixture, let's say here, and I start cooling this mixture by decreasing the temperature, the very first point at which I reach phase equilibrium is going to be the dew point. So right here is where the first droplets of liquid are going to form. Similarly, the bottom one is called the bubble point curve. And that is hard on my eyes. I'm going to zoom in a little bit. The bubble point curve is on the bottom, and that is because if I had a liquid mixture, let's say here, and I increase the temperature, the point at which I reach phase equilibrium would then be the point at which my first bubble of vapor forms. So as you can see, for a given composition and at a given pressure, that's the other important point, TXY diagrams are for a certain value of pressure. This diagram is written for 1 atmosphere. And PXY diagrams are for a certain value of temperature. This one is at 100 degrees C. So in a previous video, I said that the bubble point and the dew point temperatures were in general different. Let's take a mixture of 60%. Oh no, I erased everything. Let's take 40%. 40% benzene. And at 1 atmosphere, right, I'm going to just be along this line. The point at which I intersect the bubble point curve is going to be my bubble point. So this would be T bubble. And the point at which I intersect my dew point curve is going to be my T dew. So like I said, instead of solving those equations and constraints that I had last time, you can simply read these things off of the diagram. One more thing that you can do with these plots that makes it easy to solve equations is you can use them to find the compositions at a certain set of conditions. So on a fresh diagram, let's say that I had 40% benzene and 60% toluene. That's another point that I wanted to make is that TXY and PXY are usually plotted in terms of one of the components. So this axis down here is the overall composition of benzene. And therefore, if I wanted the mole fraction of toluene, it would simply be a mirror image of this plot. So for example, 80% benzene corresponds to 0.2 toluene, so forth and so on. So this is 0.4 toluene. This is 0 toluene, 0.6, 0.8, and 1. So don't think, for example, that TXY diagrams always slope downwards to the right, because if I were to flip this and instead plot it in terms of mole fraction toluene, it would, again, look like a mirror image. So the curves would be looking something like this. Right, and it would be perfectly symmetrical. All right, anyway, let's say that I have 40% benzene, 60% toluene at 85 C, and I were to heat that up until I reach phase equilibrium, or I was inside the two-phase region. So if I heat this mixture up, once again, at about 94 degrees C, I'm going to start vaporizing some. And at 102 degrees, I'm finished vaporizing. What happens if it's somewhere in the middle? Let's say we're at 96 degrees. What would the mole fractions that would result be? So did I say that was 96? Let's say that's 98 instead. It would help if I could read the diagram. So to find the liquid and the vapor phase mole fractions, what you do is you draw a tie line from your temperature, and a tie line is a horizontal line that is of constant temperature. So starting from the temperature of the system, I would just draw this blue dashed line, that is my tie line. Where the tie line intersects the equilibrium curves are going to be the compositions of your two phases. So I'm going to draw, these lines are just for ease in reading the plot. But where your tie line intersects the dew point curve, that is on the top, remember, this is going to be my composition of the vapor phase. So this is Y benzene would be right there. Let's say it's about 0.052. And my X benzene would be where my tie line intersects my bubble point curve, about 0.3. So as you can tell, my initial composition was 40% benzene, but now my liquid phase composition for benzene is 30%, and my vapor phase composition is 52%. So once again, vapor-liquid equilibrium changes the composition of your mixture, and that allows you to separate them or to adjust the composition of your mixture. Let's do one quick example for the PXY diagram. Let's say that we had 20% benzene and 80% toluene, and we were at 600 millimeters of mercury, and I wanted to raise the pressure until I was 650 millimeters of mercury. I could do the same thing where I draw a horizontal tie line, and where my tie line intersects my equilibrium curves are going to be my compositions. So wherever my tie line intersects my vapor phase, or my dew point curve, that's another point because TXYs and PXYs are flipped. Now the dew point curve is on the bottom for the PXY, and my bubble point curve is on the top for the PXY. Okay, so my vapor phase is going to be here, Y benzene, about say 28%, and my X benzene would be there about 14–15%. The key takeaway message from this video is that the PXY and the TXY diagram is a graphical representation of all solutions to the bubble point and the dew point curves. And from these diagrams, you can quickly solve two Raoult's laws. That's what we're doing when I'm drawing these lines, by the way, is I'm just plugging in different values and solving equations to find what X and Y are for a certain P or T. And I can flip that around too. If I know what X and Y are, then I could also find the temperature and the pressure at which those compositions would result. So that'll do it for this video. In the next video, I'm going to show you how you would draw one of these curves yourself using Microsoft Excel software.